Good afternoon, everyone, and welcome to Design Probes by Domus Academy. Thank you all for joining us. My name is Aurora Rapalino. I'm the course leader of the advanced course in Designing AI-Connected Ecosystem at Domus Academy. I'm really excited to be moderating today's talk with Leonardo Giusti. Ciao, Leonardo. Thank you for being with us.
Of course, my pleasure.
In his talk, he will explore physical AI and as a new design material. So before we get started, I just want to remind you all that we will have a dedicated Q&A session at the end. So feel free to use it as an opportunity to directly ask questions to Leonardo. I will unmute your microphone, so don't be shy. A very brief introduction. Leonardo is an award-winning design and research director, head of design and co-founder of Archetype AI. I'm sure he will explain you more about his past experiences. His work has been featured in New York Times, Washington Post, Wired, Fast Company, and other recognized magazines. Leonardo, up to you.
Thank you very much, Aurora. I'm going to share my screen right now.
Yeah.
And you tell me if it's working.
Yes.
Fantastic. Thank you very much for the introduction. Hi, everyone, even if I don't see anyone, but I'm assuming some people out there. And right, so I'm going to talk a little bit about my work over the past years. I spent a lot of time, most of my career really, working on ambient computing devices. I've done that like in academic labs, like the design lab at MIT. I've done that in corporations. I was at Google ATAP for 8 years. And more recently, with a startup that I have founded, Archetype AI. And sometimes we call this device Internet of Things. Sometimes we refer to them as tangible interaction. More recently, we talk like as embedded or situated AI. But directly or indirectly, we always refer to this vision of ambient computing, which is frankly quite old. It's like 30 years old now. And as a designer, in the design community in general, we keep talking about it as something that is about to happen. And you see evidence here and there, but I believe that it has never really fully realized. And so in this talk, I will discuss a little bit why I think this happened, or better not happened. And I'm going to propose an hypothesis that AI as a design material can actually unlock a new generation of everyday things that are infused with awareness and intelligence. So this vision, as I said, is quite old. Mark Weiser defined the vision of ambient computing in 1996, and he imagined a world where computers are everywhere, deeply integrated into what we do. And he said very eloquently, the most profound technology are those that disappear. They weave themselves into the fabric of everyday life until they are undistinguishable from it. And so, sometimes people think that ambient computing is about making computer invisible. But it's not. It's about designing computers that are so deeply intertwined with our everyday life that we forget about them. Because, if you look around, computers are literally everywhere already. They already have disappeared in the things we use every day. Speakers, doorbells, washing machine, all these devices have sensor, process information, and most of them run machine learning algorithms. However, while computers are physically disappearing into the things we use every day, they are far from being invisible. In fact, the proliferation of this computational device has caused the opposite effect. Some people refer to it as an attention crisis. We spend more time attending to these devices rather than focus on what matters to us. They interrupt us, they divert our attention, and rather than working in the background and helping us from the background, these devices actually rely a lot on direct input methods, which are predominantly like voice or touch. So as designer in this field of AI, we often ask ourselves how we can design smarter devices. But if we really want to accomplish the original promise of ambient computing, we should also ask ourselves, how can we comfortably live with computers? How can computer participate in our everyday life in a way that is more considerate? So I believe that part of the answer to this question is to make computer aware of us, more capable of understanding us and our surroundings and what we need. And as I said, my hypothesis is that physical AI could be a new design material that brings different degree of awareness to the material world in a way that is affordable and scalable. And the second part of this sentence is actually particularly important, because one of the problems with the previous generation of machine learning techniques is that they were really, really expensive, and that prevented the wide adoption of these devices, in our daily life. Anyway, I will discuss this topic by sharing two main projects. Project Soli, that I worked for about 8 years when I was head of design at Google. And then I will talk about Archetype AI, the startup that I founded more recently. So Project Soli. In Project Soli, we have designed and developed a new sensing technology based on radar to support a novel interaction model based on the recognition of non-verbal interactions. Our ultimate goal was to have computers that understand us a bit closer to the way we understand each other. So what is Soli? Soli is a tiny radar sensor that understands human motion at different scale, from finger movement to full body movement. We're very excited about this technology from the beginning because it has very interesting characteristic that make it really an ideal input method for computer living inside things and spaces. It is extremely low power. It works through material, so you don't have to compromise with the design of surfaces and finishes. It is, of course, more private than a camera because the only thing really, and I will show you, you just see bubble of energy, and it's actually very robust. For example, it works at various temperature, in different light conditions. It doesn't matter if day or night, it still works properly. Here you can see the first version. It was a very big box with 4 large antennas, and we spent a lot of time and engineering effort to compress it, all this technology into a tiny chip that now fit really into a fingernail. So this was small enough so that it could be embedded in wearables, other type of devices, mobile phones, and so on. But of course, the main challenge wasn't just hardware. From a software point of view, radar is quite complex. So the way it works, it emits radio waves. Object within the beam reflect the waves back. So, and in order to make sense of this signal and understand what people are doing in front of it, we had to invent new signal digital processing technique, as well as develop new machine learning algorithms. And at the beginning, we thought that we will get something like this, but actually, we got something like this. So it was, as you can see, the radar signal is extremely complex. We had no idea how to use it. There was no really precedent at that time about how to use radar in consumer electronic products. And we couldn't really figure out at the very beginning all the specific characteristics of this new medium, how it works, what are the limits, what are the characteristics. And so we, as a first step, we started exploring Soli as it was a new material. Rather than jumping into defining products and application, we took a step back and tried to really understand, like, what are the characteristics of this new material. So we ran several of what we internally called material studies. There are probably better names, but to explore the qualities of the reflected radar signal and build an intuition, of what interaction are possible. From the very beginning, we realized that Soli can be used to detect sub-millimeter motion at finger level. You can see here how it can distinguish each single finger and recognize very tiny gesture, like your thumb rubbing against your index finger. We ran several experiments just to understand the shape of the interactive space. Here, for example, we took a picture every time the energy reflected by this red object was higher than a certain threshold, right? And so, and by overlaying all these different pictures, we sort of like created like a map of what is the sensing space around devices. with this other experiment, we realized how the shape of the target was also a key variable. For example, your finger, when it's very close to the radar surface, reflects the same amount of energy than your palm when it's far from the radar. So this means, for example, that the same gestures will be seen differently from the radar if performed at different distances, and the resolution of the radar changes as a function of the distance from the radar. We also realized, working with our machine learning engineer, because of the properties that I just described, that the precision of the radar changed based on the distance from the radar, that we could also sense movements, larger body movements farther away from the radar. It can detect if people are there or not, and even more complicated movement, such as, for example, specific human people body language, right? But we still really, at that time, we couldn't really appreciate like what are the limits of this technology at this wider range. So we did another round of these studies. Here we draw a dot, a white dot, every time the radar detects the person. And then we had someone walking many times in the sensing field and basically draw the sensing space of the radar, which was like this sort of like oval that exists nearby the device. We also run different studies, try to understand like if we can predict with radar the velocity and the orientation of the pathways that people can take, or even how sensitive it is to tiny movement of your body. Like, can we detect with radar that you're turning around, and these other subtle body language cues. And so, we run all this study, and we realize that we have a very unique opportunity here. We can create a new input method that can capture human motion at different scales, from gestures to large movements. And so, and back to this unique capability of the radar, we could basically understand like gesture, as I said, but also body language expressions, like someone is leaning toward or turning around, and people's spatial relationships. Someone is approaching, leaving, and so on. And so we designed, basically based on this intuition, we designed a new interaction model inspired by the way people conduct their social interaction. Think, for example, when you enter a room, right, you are aware of the people around you. You may notice if someone leaves or moves, but you're not paying attention to them. And this is just like awareness. But then if you want to initiate a conversation with someone, first you need to get their attention. So you can call them by name or just establish eye contact. So we call this like engagement. And then after you establish this connection, you can start the interaction. You can start doing gestures or doing something else. So basically the model we define make the same distinction. Devices are aware of your presence when they detect the intention to initiate interaction, then switch into the engaged state. And then at that point, they're able to recognize direct interaction like gesture and then eventually respond to you. And based on this, this model, we were able to define a new set of interaction pattern. For the aware state, we were looking to detect human presence, for example, or other large movement like approaching, leaving, and so on. In the engaged state, we look for all the movements that suggest that you're about to interact with the device. So like reach, lean, and then of course the gesture like swipe and tap. So basically this model, if you really think about that, extend a little bit the traditional interaction model by introducing, in addition to the active states, which is typical direct interaction with devices, right? Introduce like the engaged state and the aware state. And so in this way, the device somehow gets ready for you when you want to start the interaction. And we modeled this, or at least we took inspiration from the way people interact with each other to model our relationship with these devices to make them more aware of us and more able to understand us even before we start interacting with them. And so with this pattern, with this library of patterns, basically, we start working with different product teams in Google to actually build products. And the first one that we built was was Pixel 4, which was like the flagship mobile phone from Google. And we work with the product team there to implement 3 of these interaction blocks, interaction patterns like presence, reach, and swipe. We started with something very simple, the swipe gestures. this is a gesture that people are already familiar with, and it's often associated with the idea of moving something away or dismissing something. And we use this for three main use cases. It was the first one with a simple swiping gesture. You can quickly dismiss interruptions, like, for example, a phone call during a meeting or dinner with friends. You can snooze your alarm without picking up your phone, in the morning and getting caught in the rabbit hole of email notification and stuff like that. And finally, you can skip song without looking at the screen, for example, when you're driving or, cooking with your friends. So basically, you can go on with whatever you're doing, getting the help you need from the device without paying too much attention to it. We also leverage other natural behavior that people already do around the phone, right? So we detect when the user walks toward the device. At that moment, we were able to turn on the screen to welcome you. And then when you reach to grab it, we triggered the camera for authentication. And so by anticipating the user intention to grab the phone, we were able to create at that time, or now it's 4 years ago, 5 years ago, the fastest authentication experience in the market, which was pretty cool. So then we expanded our work into other products. We also work with Nest Hub. They were interested in particularly in two types of gesture, the swipe and the tap. And we expanded our gesture vocabulary at this point using this special model where we use the x-axis for content manipulation to swipe, to move things around, and x-axis to take action, to initiate something. And here was implemented like similar use cases, you can swipe to dismiss your alarm in the morning, and you can do the same for music, or tap to play and pause. I also want to show like a little bit more like research work that we did at the time as we were working on the products. We were also working more on these different states that I was talking about, the awareness states and the engaged states, and we were developing new algorithms to really capture these different social cues that we use, around other people. And the result of this work is this video I'm going to play now. Do you see it?
Yeah.
Today, computers are everywhere, but the more devices we have, the more overwhelming it can get. So advanced technology and projects team, Google, is rethinking how we interact with computers. We're using technology and advanced machine learning to create ambient, socially intelligent devices that are controlled by a wave of a hand or turn of the head.
We are inspired by how people interact with one another. As humans, we understand each other intuitively without saying a single word. We pick up on social cues, subtle gestures that we innately understand and react to. What if computers understood us this way?
This is where solid data technology comes in. We are using this motion sensing to enable the device to understand the social context around them. The device can sense when someone is approaching or entering its personal space. The overlap between the two personal spaces is a good estimation of the social relationships, as well as the level of engagement between the person and the device. Our technique uses advanced algorithms, including deep learning, to understand the nuance of people's subtle body language.
Our machine learning algorithms can estimate head orientation. This looks at the angle of a person's head to approximate where a person might be facing, and therefore what a person may be paying attention to. This allows us to make more accurate predictions of how and when a person wants to engage.
Our observations of these detection algorithms led us to design a set of interaction primitives. So there's approach and lead. This allows a device to understand when it's the right moment to initiate a conversation. It's also important to understand when a person is just passing by, so the device can avoid interrupting someone when they're doing something else. With turning towards or away, we can create a more natural dialogue between people and devices. And with glance, this allows the device to understand where a person may have their attention.
All these nonverbal interactions allow for a better, more harmonious integration of products in our everyday life. These devices are designed to cater to us from the background in a quiet, respectful way. You can get these gentle prompts and have interactions that are helpful, but not obtrusive. And the technology has enough context to recognize your subtle cues and adjust to your needs within the moment.
See you tonight. Bye.
As computers continue to disappear into everyday objects, we are imagining a future where products have a social intelligence. The experience can be quite magical. We have devices with social grace to make them understand us and participate in our everyday life in a more considerate and delightful way.
All right. So about 12 months ago, I decided to leave Google to found my own, with some coworkers, you will recognize some of them from this video, to start our own startup. We call it Archetype AI. We did that because we saw an opportunity in recent AI advancement, in particular in the transformer architecture, as a new approach to solve some of the scalability problems that were affecting ambient computing technology and more in general, any sensor-based technology. So what is this problem? The problem is quite simple, which is like developing customized machine learning solution for sensor is extremely expensive. It is very time consuming and it actually very difficult. Very few specialists are able to do it properly. So this is an example of the resources we needed to develop one single gesture for Pixel 19 at production scale. And this is important because building prototypes is quite easy and straightforward, but when you have to ship it into a product used by millions of people, it just the bar is so high that get that level of precision and accuracy, it's really, really hard. So as designer, we were involved in defining these more than 300 cases for data collection. You can imagine them being like different ways in which people can swipe with a flat hand, with two fingers, with vertical hands, with different speeds. We took into consideration age differences. An older person swipes very differently than someone that is 16 years old. And so we have to collect all the possible ways in which people intentionally do a gesture, but also all the negative case that they may look like a gesture, but they're not like a gesture. Like, for example, this cup moving from the left to the right of the phone. And we call it the red cup test because we weren't able to solve this just like 1 month before we actually shipped the product. It was really, really hard, but we had so many of these and you have to collect so much data to teach the model to understand all the tiny differences in the signal that will allow you to make this distinction. So in total, we collected something like 5 million gestures, and we had to do it with about 8,000 participants in 9 locations all around the world because we had to take into consideration cultural differences, different ways people in different places may do gesture or behave around phones. So it cost a lot of money and it was years and years of work. And then you can imagine that, okay, now let's do it for Nest devices. You have to redo it from scratch because it's a different device, a different orientation of the sensor. It just like, of course, we knew at that point how to do it, so it was a little bit faster, but the amount of work was the same. It was as complex and as hard. So it's clearly is not sustainable or scalable, not even for a company like Google that has a lot of resources to do these things. So the challenge here with traditional machine learning approach is that you have to build this machine learning model for each specific use case. A new use case requires a new model, more data, more training, and so on. So, and now that we are, the number of sensors is rapidly increasing in the world, this approach is clearly no longer sustainable or applicable. And that's why we founded fundamentally Archetype AI with this idea. Can we build one foundation model for the physical world to serve all use cases across all verticals and data types? It's a very ambitious project. In other words, can we build GPT for the real world? As you know, the large language model can be fine-tuned to do very specific tasks with minimal data. Training them is very costly and take a lot of time. And once you have it, then you have these things that allow you to very quickly scale to many different use cases. So our hypothesis is that if we build such a foundation model to interpret sensor data, we can then easily tune it towards specific use cases without retraining it from scratch. And that is why we founded Archetype AI with 5 co-workers from Google. And here what it is, I will play another little video that will explain what we are doing better than I will do.
Archetype AI is built in Newton, the first foundation model that understands the physical world. It fuses complex sensor data with natural language to understand and reason about what's happening in the world around us. We call our technology a large behavior model because of its ability to reveal the world's hidden patterns of behavior that are beyond our perception.
Our vision is to encode the entire physical world. Newton is one foundation model for all kinds of sensor data beyond basic text and images, from radar to inertial sensors to chemical and environmental sensors. These different types of sensors reveal different aspects of the world, phenomena that we, as humans, can't directly perceive. Combined together, this will give us a complete understanding of the physical world around us.
At the core of Newton is a universal embedding space that fuses sensor data and language. The traditional approach of building a custom model for every sensor type misses critical insights because each sensor is analyzed independently. Our universal embedding space integrates all sensor data into a single compressed mathematical representation of the physical world, updated in real time.
By fusing it with the mathematical space of large language models, we can compute the meaning of sensor data using basic mathematical operations. We can then decode this data into any form that helps humans understand it, such as text, visualizations, or code.
New instruments require new modes of interaction. We are proposing semantic lenses as the interaction metaphor for a physical AI that is continuously engaged in the real world, microsecond by microsecond. You can easily focus the model on what's important to you by adjusting the focus of the semantic lens using natural language. The real world never stops. Unlike current AI systems, you can't just type a question and wait for an answer. A semantic lens is continuously decoding sensor data into a stream of insights, suggestions, and predictions that anticipate future events.
The world's biggest problems are physical, not digital. Our first developers are already using our model to solve real-world problems. In our design partner program, we have an automotive company fine-tuning our model to give vehicles real-time situational awareness. We have a construction project reducing waste while improving worker safety. And we have consumer electronics companies enabling the next generation of AI-first devices.
Archetype AI's large behavior model coupled with Infineon sensors will enable new intelligent devices such as smart cameras, smart TVs, and electronics that we use in our everyday lives to make the electric more intuitive.
In Newton, any physical business can become a business with AI at its core. We invite you to join our design partner program and explore how can we see the world through the lens of physical AI.
Right.
Archetype AI is built in Newton.
All right. So what we are, as Ivan said multiple times, we are building Newton. Newton is our proprietary foundation model that can perceive and reason about the physical world in real time by fusing multimodal sensor data and natural language. The way it works, very briefly, we are projecting sensor data into the same mathematical space that a large language model, which means that now we can translate any signal into meaning. Basically, we can use what the model knows about the world to make sense of what's happening in the real world. So this means that once we have done that mapping between a sensor signal and the semantic embedded into a large language model, then we can basically interpret the signal and fine-tune the model using natural language to do very specific things. For example, here it was one of our first experiments where you can see how the model is mapping sensor input, which is a camera, into a description. It's simply mapping what it sees into a description, a textual description. For example, there is a person standing behind the table, holding a tea maker, and so on. What is interesting is that we were able to do this with other input signal as well. And in this case is with the radar. You have seen this in the video, but if I can pause 1 second, what you have here is like on the left, you have the raw signal that is projected into the embedding space, which is like the middle screen, and then decoded into a description, which is what you see on the right screen. So the model is basically taking a signal, compressing to the embedding space, and then decoded it into a textual input. When we in April this year, we exited stealth, and there was an article on Wired by Stephen Levy about what we are doing. I personally don't like the title, but the subtitle is quite accurate. Archetype builds AI model that can act as a translation layer between humans and complex sensors, using plain language to help people understand what's happening in a building, car, or human body. And so our belief is that once you have this single foundational model, this will enable us to quickly scale and develop a variety of use cases in different verticals. We are already exploring pilots in, of course, smart homes, vehicles, but also healthcare and monitoring your healthcare over time. Because once we are able to make sense of sensor signal, then it becomes straightforward to build product and application on top of it. And as I said, while today we are talking mainly about ambient computing device in the home, etc. But for us, it's actually very important, and it seems very promising, the application of this technology in industrial sector. We have a lot of interest from companies work with heavy machines, for example, that are very expensive and they can afford to stop them, or like construction site or any type of big building that need to keep their workers safe, for example. Or even there is a lot of interest from energy infrastructure and people that are working on creating more sustainable energy, where having this model, analyzing the sensor continuously, will allow them to do these things they call predictive maintenance, for example, or predicting when something's about to break, for example, and so on. So these the way I like to think about these what we call physical AI is truly like as a new material that we have now available that can unlock different use cases and opportunities, both in the consumer electronics environment, but probably as a starting point, I think the true application will be in the industry and working with companies that have serious problem about supply chain, manufacturing, energy, and so on. So, as a design team in a startup, before jumping to design specific products or application, we decided to do something similar, something that we did with Soli as well. We decided to take a step back and really study physical AI as a material to truly understand and have an intuition of what we can actually do with this new thing that we have. So we start studying the material property of AI. And we run a set of studies that I will show in a bit to really try to understand how we can design an interaction model for physical AI that reflect its unique qualities, but also leverage concepts that are familiar both for developer and end user. Because if you look at what we do today with AI, most of our interaction with AI are mediated by the metaphor of the assistant, right? And the interface are based in a way or in another to these typically messaging apps. And what is interesting to me about this is not just a superficial aspect of modern AI. It is not just the UI or the surfaces. It actually, the way these material, the generative AI material, has been structured. Because if you look a little bit deeper, and if you start to look, for example, into the APIs that are available to the developer, you realize that they have been built around the idea of assistant as well. What a developer does by calling different API function is actually building an assistant so that a user can chat with this assistant via messages. So the idea of an assistant and a chat based on an input-output is not just a UI thing. It's actually how the API, for example, of OpenAI are actually structured. But even deeper, the way these models are trained, they are trained in this format that is called the alpaca format, which is structured like this. You give an instruction, then you give an input, and you receive a response. So they are specifically trained to answer questions given certain instruction. So the entire system end-to-end is built around this idea of back and forward. I ask you something, you give me an answer. And that's how it's structured, from the model, the API, through the interface. So the question we should ask ourselves is, like, as designer, that we are developing new product with AI in a slightly different domain, the physical world, is this the right approach for physical AI? And so we believe that generative AI and physical AI are quite different, even if they share some very similar technologies. In generative AI, you ask a question, then you wait for an answer. The AI is reporting back on what it has learned from a huge amount of knowledge, static knowledge. And so the idea of an assistant and a chat interface sort of makes sense. In physical AI, it's a quite different situation, right? Because first of all, the AI is continuously prompted by sensor data, right? And it's continuously decoding them into a stream of insight. As I say in the video, the world never stops, right? And there is no reason to wait for the next question in order to get the information that you need. This means that the role of the user is quite different. It is not asking question and receiving answer. It's actually to steer or bias the interpretation of the data while they are still working on the physical world. This means that the physical AI is also differently from generative AI, is actually situated in space and time. Right? Different from generative AI is location matters. If a sensor is in this room or in another room, the same prompt will probably generate very different answer. So where is situated, both from a space and time point of view, it truly matters and affect the way it works. And of course, the context, the social context around the AI, the meaning of a situation also should affect the way the data are interpreted. Anyway, so metaphorically, we start referring to physical AI as it was a lens. Like an optical lens, it allows you to observe the world and discover patterns that would otherwise escape our perception and cognition. I like this picture because Newton is not just our model, but the real Newton was using a lens to understand the property of light. It was a prism. The white light was decomposed in multiple colors, so he could see the different frequency of the light that weren't visible to his naked eye. And so he was using a tool to reveal patterns that were not available immediately to his senses. And so we believe that physical AI play a similar role. It play a similar role. It capture. We believe that this idea of a lens captured the core idea that physical AI mediates our relationship with the physical world by decoding sensor data into a continuous stream of information. It also helped ourselves to position physical AI slightly different than generative AI. Our vision for AI in general is that we believe it more like as an instrument that augments human intelligence rather than replace it. And the idea of a lens as a tool fits this vision quite well. And so what is interesting about this metaphor is that give us a language to start exploring physical AI as a material. And it allow us to identify some key concept. For example, this idea of focus that I'm also talking about it during the video. And this idea that you can focus the model on what is important to you by adjusting the focus of the lens using natural language. And here is one of the demo, just a little bit longer version of the demo showing the video where the user can adjust the focus of the model using natural language. For example, right now, Newton is monitoring the transit status of an hypothetical package. And you can see how the interpretation of the data stream is the package is in motion, the package is still, but then you will see now the user, which is me, is going to change the focus to package mishandling. Then run the lens again. And now the interpretation of the data completely changed. Now the model tries to understand when the package is shaken, when the package is still, or the package is handled gently, and so on. I want to say that it's not that we are using a different model, or that we have trained the model for this specific prompt. It's exactly the same model. We are just able to steer the interpretation of the data by changing its focus using natural language. And just we're running out of time, but here another simple example using camera rather than accelerometer, where we ask the model, for example, to understand the vibe of different rooms, and he's able to translate, a certain image or video into simple, I don't know, vibe of what that room means in a certain context. And then you can simply change the focus, for example, describe the neighborhood you are in, and now the model will actually provide a description like, okay, what neighbor is this? And it gives you so it's the same idea. It just like by changing the focus, you can bias the interpretation of data, and this data can be IMU, camera, radar, or anything else. In the future, our vision is that we can encode all different types of sensor data. But of course, we're also exploring a different aspect of the model, is like, can we actually output a visualization rather than just like a textual screen? Here, you see, the model is able to generate heat maps. In this case, we say, okay, focus on the car in front. And so it only focuses on the car in front and ignore all the car nearby. And now we change the focus and say, okay, now focus on pedestrian. And at this point, the model is able to create a heat map that highlights the presence of people and ignore any other things. So we can direct the attention just using natural language. And this is, once again, I'm going to repeat it. It's not in the past, in order to do this, you have to train basically for 2 use cases. You need to collect a huge amount of data for cars and people and so on. Right now, once you've done the mapping, you get all these different use cases for free. And I want to show 2 last things. As we are running this experiment to really understand the properties of this model, we realized that once you map a sensor signal with a large language model, you can leverage what the model already know about the world to make sense of that sensor signal. For example, here we ask the model to predict the next steps of someone making coffee. And because the model somehow knows the step of making coffee, it can simply suggest you what's next. It's not that we train the model to do that, but we find out that there are these sort of like structure of knowledge that is already embedded in this model that we can leverage to do different things, like, for example, predicting what to do next. See, now you have hot water, the next thing is to steer. Then after you steer, plunge and serve, and so on. And the same experiment, like, can we leverage the knowledge that the model has about the world to understand anomalies, which is a very important thing that we have been asked from in many different contexts. Can the model understand when something is not right? And because the model knows a little bit about our world, because it has been trained on these things, now it can make this distinction, realize that an apple doesn't belong there. Yeah, so we are still at a very early stage with Newton. We are just running experiments now. In the next future, we are building now POCs, proof of concept, with some partners to bring it to life. But yeah, this is just a first introduction to the model. So just to summarize, like what I've talked today, I believe that, my hypothesis that ambient computing vision has been slowed down by technology limitation, the unit of economics that I discussed before. with existing machine learning technique is simply too expensive to scale it. And I believe that artificial intelligence, and in particular physical AI, is going to overcome some of these limitations and infuse the material world, the things we use every day, with different degrees of awareness. But third, and this was a little bit of a thread, I didn't explicitly talk about this, but it was a thread throughout the deck, is that I will argue that if we want to make this new thing, this new everything right, we need to get our hands dirty as designer and try to shape, if possible, AI itself as a new design material and not just the product coming from there. So in other words, we need to play a role at the early stage of research and development. And that's at the end of the day why I like to do what I do, work in this weird position, but also the main reason why I'm one of the founders of Archetype AI. Done. Thank you very much.
Thank you, Leonardo. It was very inspiring, especially because you also explained the process behind, no? Each time that you step back, something happened. So thanks. If you have any question, please raise your hand and I will unmute the microphone. Connecting to the last part, the last remark you made, I've seen also in the video you share and on the website, this statement that for me it's really clear and I was like, whoa, yeah, that's true. AI today has been reduced to a chatbot. The biggest problems in the world are physical, not digital. Can you explain a bit more? Because I think it's the base, no, of what you are doing.
Yes, that's at the end is the key vision, is the vision of, well, not the vision, is the mission of Archetype AI. Our mission is to use the power of AI to help people to make sense of the world. And this was one of the main motivation why we left Google. We were seeing so many interesting AI applications, but they were all applied to the digital world, you know, like what's happening on internet and all the generative AI. They're very powerful techniques, but they're all related to what's inside the screen. And so at the end, we say, can we use this amazing technology to actually impact what's happening in the real world? Because at the end of the day, there is a lot that's happening outside screens that is very, very important. I mentioned some of these use cases like healthcare, for example. Like if we could take data from our body in real time, different sensor, and interpret them in real time, this is pretty huge, especially if you can combine them with your, for example, clinical data, right, that are already there. If you can combine this different knowledge that you can capture through sensor with what we know about something like your body, for example, then you have a very rich understanding of what's happening. So our belief is like we can truly use AI to have an impact in the world and really affect important problems. There is another statement there that is like and I touched a little bit on it during my talk, that it's like the interaction with AI has been reduced to a chatbot. Mm-hmm. Which is true, and that fits, you know, when you interact with something, when the stage of interaction is your screen, and the moment in which the stage of interaction shifts from your screen to the real world, we need to rethink the way we interact with this physical AI, and that's why the exploration.
Mm-hmm. So yeah. If we are keep just on looking at our screen, of course we cannot imagine and conceive new way of interaction, no? So
right.
That's true. Yeah. You mentioned before, but I'm a bit curious about your career path and what led you to move from roles at Google or Samsung to co-founding Archetype AI. We have many students here, so I think might be very interesting for them also understand your career path.
Yeah, I mean, I didn't have a very clear career path. When I started college, I really didn't want to be a designer. I really didn't even know what design was at the time. I joined, actually, I mean, Silvio and I share a lot of we have a lot of commons. We studied at the same university, the University of Siena. And at that time, I was really into the cognitive science. That was very interesting for me in psychology. But while I was doing my PhD there, I had the opportunity to work in several projects in collaboration with Domus Academy and with Claudio Moderini, which really was my mentor at the time and completely made me understand what design is and what it means to be a designer. And that was what clicked for me. During that time, I really got really passionate about design and interaction design. And during my PhD, I was working in several projects I mentioned with Domus Academy, actually. And that's when everything clicked for me. And I decided I want to be a designer. And I had the opportunity after that to, I mean, the story is simple. I was at the Festival of Creativity in Florence, showing my stuff that I was doing during my PhD. And at the time I met Federico Casalegno, which was like the director of the design lab at MIT in Boston. And we had a nice chat, and a year later invited me to go over there. And that's basically how I moved to US. I did my postdoc at with Federico at MIT for 2 years and a half, 3. And then at the time, I start to realize that being a designer, you really need to be a practitioner. You know, if you really you really need to make things. And I was like getting a little bit bored of just writing papers, and then your work sort of like
You wanted to get your
disappear.
hands dirty.
Yeah, I really want to do the thing. And so I got the opportunity to move to San Francisco, where I started to work with Samsung for the design, what's called advanced design team, something like that, where we were pitching new concept for Samsung product. And then I met, I had, you know, once you are in this environment, there is you meet a lot of people, a lot of connection. And I met Ivan Pubirev and invited me to join Google ATAP. And then I spent there 8 years, and that's how I ended up there. And then with the people at Google ATAP, we were a very tight team. We were sort of like little islands inside Google, where we were doing a lot of very special projects. And after 8 years together, we decided that was the time for us to branch out and do something new. And basically me, Ivan, Jamie, Nick, and Brandon just left together and created Archetype AI.
And what's the next big milestones for Archetype AI and Newton?
Well, the next biggest milestone to make it work. And so, and now it's in prototype phase, and we are building it. But I think by the end of the year, beginning of next year, we want to prove that Newton is running. We have this idea that we want to show that Newton is able to understand physics, and so what's happening in the physical world, that is able to not only, you know, describe what's happening, but truly understand the physics of things, you know, and predict things based on this understanding. And then in parallel, as we're building up our model, our foundation model, we already started to work with industrial partners. It's always been a thing of us since when we were at ATAP. We were always had these 2 parallel tracks, the R&D tracks and the more commercialization path.
Mm-hmm.
And there was a continuous back and forward between the two, because you realize if you only do R&D, the space is so large and vast that very easy you find yourself lost in some corner and no one care about it. If you only do commercialization, you just do iterative stuff. You just you know, you just do the next little thing.
Yeah,
and
you
if
have
you
to
are
find the balance.
to have both, you can push your partner to really think differently, and then your partner can push you to actually focus on what matters. And so hopefully in the next few months, by the end of the year, we will have 2-3 partnerships that we can show the world that we have built with Newton.
Finger crossed. I think that we can move to the Q&A session. So if you have any question, please raise your hand. Okay, I see one. Mohammed, please.
Hi, Leonardo.
Hi.
Thanks for the amazing presentation. My question was actually, so as we students, right, we have been coming across a lot of things related to AI, and also there's this confusion that AI is harmful as well as like it's a boon. Uh, so Coming from one of previous sessions that we had with Christopher Nozel, where he explained like descaling, like at AI. So, so it's something like when we have like over reliance on AI, we as humans we lose ability, to perceive like the normal functions that we do. For example, the car example that you showed the video where it detects everything. So what if like somebody is like over reliant on that, and maybe you get that person in a different environment and that not able to perform the way that it should be? What is your take on that?
Sorry, maybe Aurora, you can help me. I'm not sure. I couldn't hear very well, so I'm not sure I completely understand the question. But was it the question about what happens when AI fail?
It was more of like over reliance on AI as humans. So in the process, then we lose our own ability like to perceive things, and then we are like more dependent on AI like to do things. And in the long run, maybe we as humans won't be able to perform that kind of function, and it kind of diminishes our own ability.
Yeah, understand. That's a very interesting question, actually. Yeah. It's a very complex question, you know. It's not just, is it just about AI though? Can this question be generalized to every other technology? Which is still a very interesting question, right? How technology, as we rely with technology, how our cognitive function can be become more and more dependent on them, and so we lose some of this capability. For example, like a classic example is Google Maps. I used to be I lived in a world without Google Maps, and I was able to orient myself in cities after a while, recognize landmarks and so on. Right now, I've been living in San Francisco for 12 years, and I can barely go around without Google Maps. If Google Maps is down, and it happened once, for a few hours it was down, people were panicking all over the city because no one knew where to go. I think AI and the rest of technology, yes, I think it is part of, I would say, of the relationship between people and technology, but it's also like what makes us human in a sense, right? I mean, what makes us human is actually the fact that we can use technology, that we can use technology in a way that amplify and augment and change our relationship with the surrounding world. So it's a little bit of like, on one hand, this technology amplify what we can do in the world. On the other hand, I think there are some changes that are necessary in the way we perceive and understand the world at a cognitive level that happen in relationship with technology.
But it's gonna take time, no?
It's gonna what?
No, I say it's gonna take time.
Yeah, of course. These are processes that probably take years and years, right? To change and adapt. Yeah, I'm sorry, I don't have a very straight answer. It's more like a set of considerations that I do believe that this relationship with technology is something that started when, maybe 10,000 years ago, when humans start to use tools, right? And the way their brain has changed over time because of the use of tools is something that led us where we are today. And so I think that in artificial intelligence or any other technology, it's going to keep changing us as we shape the technology. The technology is going to shape us and our cognitive system and the way we work and we remember things For example, memory is another one that is clearly affected by technology, right? Going specific about AI, the way I try to see AI, I try to see, and this comes, there is not a right way or a wrong way. It's more a vision or a point of view. And I believe I try to shape, we try to shape AI as a tool, as an instrument in the hands of people. And ultimately, people are in charge and in control of what the AI can do for you. A different vision is this idea that AI is this peer or this entity that works with you and which has more agency in a sense and can do things by its own and so on. So
but it's a completely different way, no, of seeing AI and using AI as well, no?
Yes, yeah, exactly. Using and seeing and perceiving it and the type of relationship we can establish with them. I'm not saying that one is right and one is wrong. They just have different affordances in a sense. And these different visions lead to different solutions, you know, and the way you apply AI to the world.
And different interaction. Yeah, true. Any other question? Don't be shy. I have yes. I see Renzo Giusti. Ciao, Renzo.
Renzo, oh my God, Renzo.
Renzo, I'm trying. I don't know why it's not working right now.
I should be unmuted right now.
Ciao, Renzo.
Hello, Aurora. Pleasure to meet you again.
Yeah, for me as well.
Long time no see. Just a question, because it got me very curious. It's since the beginning of the year that I've been gathering information about AI and what it can and what it can't do. And it's a very insightful what you and your team are trying to do, because right now, as you mentioned, everything is focused around mostly picture production and text production. But basically, it acts as a disembodied entity. And a lot of people were commenting previously about this fact that the current AI that's being mass used lacks physicality. What you showed us today basically builds upon this missing part. And in your vision as a designer, what you foresee that this that you're working on is basically enabling AI to build up, and what do you think it will unleash in the future?
Yes, yeah, I think that's a key point, and I briefly mentioned about it. This idea that as AI become able to perceive the world, it becomes situated, which means that now it exists in a specific location in space and time, which means that the context in which the AI is truly matters. So, for example, a certain gesture, even if it's in the same space, may mean many different things if the context is very different. So this is one of the key challenges that we are trying to solve, is like, when AI is situated and understand the world around it, how can you actually make sense of it if you don't understand the context? Can the AI understand the context where the sensing is happening so that it can actually provide the right information? And we have some interesting initial results that, because we are leveraging some of the knowledge already embedded in the LLMs, it's sort of like there is an opportunity there that we haven't seen in the past, that the AI can pick up some of the little cues, subtle cues that we have in social context in the world around us to actually build a model of the world around it. So the way I'm envisioning this embodied AI in the future, I think there are fundamentally, I can see three main scenarios here. One, this AI, as I mentioned, becomes a layer between you and the world.
That's,
And this is become a way for you to discover patterns in the world you couldn't see before. And you can see these like application in like security, manufacturing, or even science and discoveries and stuff like that. So it's this relationship where the AI is a layer in between you and the physical world. There is another, let's call this the instrument bucket. There is another bucket where the AI completely disappears in the environments and become part of the building you are in. So you don't even directly interact with the AI, but the AI makes these spaces adaptive. And we have one on POC that one how do you call them, like HVACs, you know, the one that make your room cold, or that if you do this at scale in large building, you can truly optimize the energy, right? Because understanding where people are, where they're going, what they're doing, the AI works in the background to optimize, for example, the comfort in this building. But this is more like sort of like the AI becomes like invisible. It moves like it's an engine that moves into the background. Then there is like I can see a third bucket, and we've seen some little example of this. I think the best one is I think you guys have talked about this is the poem clock by Matt Webb, but there are other commercial things where AI becomes part of an object that is there with you. So you have a sort of like direct interaction with the AI, but it's not a lens, so it's not something between you and the world. It's more like a peer, a partner that you work with in the world. So it is embodied in a physical shape. And this, of course, in its extreme, is called robotics. And right now, the biggest conversation in Silicon Valley right now is around robotics and how AI is going to shape robotics in the next year. But I believe there is a simple version of robotics. You know, robotics is really like, oh, yeah, this guy going around. But there is simpler version that are like of robotics that are like can be like small devices that have some very simple actuator that exists with you in an environment that doesn't need,
life.
Yeah, in everyday life, that doesn't need to be like a machine.
Any other question?
No, we are not brothers, but we do have the same surname.
Okay, Leonardo, thanks a lot. And thank you, everyone, for joining us. And I hope you enjoyed as much as I did, because it was really inspiring. And again, the fact that you show the process really make us understand also the part that might not be easy, no? So the exploration, the experiments, you can see there is a lot of work behind, and that you really truly believe, and we do as well. So thank you.
Thank you.
Ciao, thank you, everyone.
Ciao.